Before we start, I just want you to watch this little animation. So that may not have made a lot of sense, but we're going to watch it again at the end, or I'll just leave it playing after the lesson's over, and it will probably make a lot more sense then, and it's a nice little visual. So I talked about this before, how basically we're redoing all of grade 11 trig again in grade 12, but with a grade 12 twist to it. Now, we are gonna add some new stuff as well, so there will be other things that are new. But a lot of it is going to be very similar. But in grade 11, you use degrees. And in grade 12, we use a unit of measurement called the radian. Okay? So, as it says here, up to this point, we have always measured angles in degrees. Like even in grade 9, when you're doing work with angles, it's all in degrees. And that's a normal way of thinking about things. We're used to it. By definition, there are 360 degrees in a circle, and that's what defines the unit. So what is 1 degree? Well, 1 degree is one slice of a circle that's been split up into 360 equal parts, right? That's the definition of a degree. Why 360? How come not 100? Why do you think they did 360? But it goes all the way around 360 because we defined it that way, right? Anybody else have an idea? I'm not expecting a right or wrong answer. Do you have a guess? Why they chose 360? Does it seem like an odd number when you think about it? No? No guesses? Jasper? That's a very good guess. That's 360 is a very nice number in math because it's so divisible by things. Like 36 has a lot of factors, right? Well, 360 has that many more factors. 5 goes into it, 10 goes into it, 20 goes into it, right? 30 goes into it. Like all these numbers divide into 360. So it's very divisible. So that is one of the theories. I don't think we know why we picked 360. Why there's 360 degrees in a circle. But that is one of the theories, is that 360 is just a nice divisible number. Some people often think, and often you'll get a student who guesses, well, is it because it's kind of close to 365, and 365 is like, us going around the sun, so that's kind of a circle thing. But then they rounded it to 360 because it's a bit of a nice number. It's possible, but we don't actually know why 360, but that's what we have, and that's what defines a degree. And you will think that degrees are easier because it's what you're used to, because you've been working with them for so long. So you just kind of get degrees, just like most things that you've been working with for your whole life. When I say 30 degrees or 45 degrees, you can kind of picture that. 90 degrees, that's a right angle. You're used to those numbers. You're used to that unit. So that's part of what is going to make working with radians harder. But there's another side to it as well that makes it harder at first. Okay, but this is what we're doing. So a radian is a different unit of measurement. Folks, this is just like you can have a centimeter or you can have an inch. And an inch is bigger than a centimeter, and 1 inch is one of that unit. And 1 centimeter is one of that unit, but they're not the same size. So it takes more centimeters to make up an inch, right? This is the exact same thing as degrees and radians. A radian is bigger than a degree, and it's just a different unit of measurement. Okay. It's useful. It has no unit. It's not exactly true. I mean, it is the unit, but it's a ratio. So that's what makes it useful. as opposed to a degree, which is just a defined unit. A radian is actually a ratio that defines the unit. Okay, it's a ratio of the arc length of a segment of a circle to its radius. So this means that it plagues high school math students all over the planet, but it's really, really useful way of doing this kind of math once you get used to it for mathematicians and physicists and engineers who actually use this stuff. Okay, so my analogy for working with radians, and this comes up a couple of times in this course. It comes up in this unit and unit 6 as well. When you learn a new language, it's really hard at first because you just don't know any of it. And how many people here speak more than one language? Okay, a lot of people, yeah, almost everybody. So if you think back to when you first started learning the second language, you maybe you don't remember, maybe you were very young. It's different if you're very young probably, but if you're a bit older, you start by translating everything into your native language or your more familiar language. So I learned French. I was in French immersion when I was in school, and I have vague memory of this, that when you first start learning French, somebody says a word, you translate it to English. This was my experience. Think about it in English, form your response in English, translate it back to French, and then say the response in French or write the response in French or whatever, right? But all the thinking happens in English or whatever your familiar language is, and you're doing that translation back and forth. And then all of a sudden, when you become fluent, and they say that this is like a sign of becoming bilingual, when you start thinking in the new language. And at one point in my life, and it was a long time ago, so I'm not used to French anymore, but I would think in French. And if I was in French class, I would just be doing everything in French and thinking in French and working in French. And it was just like you are now just using that language and sort of, fluent in that language. And so, and there's that transition period, and you don't necessarily notice it. It just kind of happens. And that's what's going to happen with working with radians. At first, you're going to be doing a lot of converting and thinking in degrees. But I'm going to encourage you to practice with radians as much as possible and try not to always be converting back to degrees. And eventually, and you might not even notice, and all of a sudden later in the unit I'll point it out and you'll be like, oh yeah, that's true. I don't even think about degrees anymore. I just think radians. And that's when you know you're kind of ready for the test and you're kind of getting it, and you're going to find the work a lot easier if you're not constantly converting back to degrees. And my rule will be, on quizzes and tests, I don't want to see 1 degree symbol or 1 degree measure on the entire thing. Everything has to be in radians. So if you get to the test and you still don't understand radians and you're converting everything to degrees, you have to do that on some kind of separate paper and make sure I don't see it. Okay? And you can try to fool me that you're actually doing it in radians. But most of you will, by then, be fluent in radians. So that's your challenge. So I only say this because it's a warning that at first it might seem very difficult. And the struggle is that you're learning this new unit. But eventually you're going to get to a point where it becomes easy. As long as you work through it and do the practice and all that stuff, you'll get there. Just by using it, just by like immersing yourself. Like if you go to a new country and you just live there for a while, you'll learn the language because you just kind of have to, right? So same thing. If you just immerse yourself in this work, you will get there, but it will seem hard at first. So what the heck do we mean by ratio of arc length to radius? That seems like a strange little phrase and it probably doesn't make a lot of sense. So let's explore it. So we're going to do 3 different ones. So here's our radius from there to there, right? That's the radius of the circle. Arc length is some kind of length. So you can see that I've marked a thicker black part of this circle. So that's our arc length. We're going to call that A. So what is the ratio between A and R? This is what we're talking about. So arc length is some part of the circle. It could be the whole circle or it could be just a part of it, right? The length of an arc on the edge of a circle. So what would you say is the relationship between the arc length and the radius in this case?
1 radian?
Nope. Good guess. What I mean is the arc length longer or shorter than the radius? Just by looking at it, I think you can tell. Shorter. So you would say A is less than R? Would you agree with that, everybody? So if I kind of rearrange this, then A over R, we don't have to worry about dividing by R because R is a length that's always positive, so don't worry about flipping the sign, is less than 1. The ratio of arc length to radius is less than 1. You would agree with that? This is what we mean by ratio of arc length to radius. Okay, what about this one? So here's my R. Here's my A. What's the relationship in this case? I think it's obvious. What do you think?
A is greater than R.
I think so too. It looks quite obvious that A is a lot greater than R. So again, if I divide by R, A over R is greater than 1. The ratio of the arc length to the radius is going to be greater than 1. For example, if the radius was 1, that arc length might be 3.5 or 4. So it'd be 4 over 1, which is bigger than 1. Okay, and the last one. So here's our R. Here's our A. What do you think the relationship is between them this time? Who would like to guess?
A equals R.
They're equal. Exactly right. And I know they're equal because I used a program that was able to actually calculate it and set it up to be equal. So not only do they look equal, and it's maybe just a good guess, they actually are equal. And so that means A over R equals 1. What do you think this means? That's 1 radian. That's the definition of a radian. The angle that is measured when you like spin one radius away from another radius or something like that, if you think about it like that, kind of like angles in standard position like we talked about yesterday. And you get to a point where the arc length is equal to the radius. That's what defines 1 radian. So this is 1 radian. So again, comparing it to degrees where they just picked a number and they said, hey, let's just go with 360. And then they evenly split the circle up into 360 parts. But it's kind of like random because they could have picked any number. This actually has a meaningful definition. So as it says here, by definition, 1 radian is when the arc length is equal to the radius. And as I said earlier, this turns out to just be a convenient way of doing things. It just makes math work out nicely. Now you're going to disagree with me at first because you're going to be like, this doesn't make it nice. This complicates everything. It was easier in degrees. Well, it's easier for you in degrees, but once you get used to radians, the math is nicer in radians. Okay? Okay, so in this lesson, we're going to explore a couple of important concepts. We're going to talk a little bit about converting, although converting is not really what we're going to do throughout this unit and the next unit. Converting is something that we're going to do maybe in the beginning, but we're going to get away from it very quickly, or we're going to try. And we're going to do a couple of other kind of little questions, but really the important part is getting used to some of these important numbers in radians, which if you look at the back of your sheet, which you don't have to right now, but we have a little chart, that's going to be kind of the big part of it, and what we're going to do right now. So I'm going to start with, anybody know the equation for circumference of a circle? Everybody says pi r squared, that's area. Danielle? It is pi times diameter. I'm going to use the radius instead, but very good. So circumference equals 2 pi times the radius. Because 2 times the radius is the diameter, so it's the same thing. Very good. If I want to explore the number of radians in a full circle, then I would make my arc length the entire circumference. Okay, so full circle, arc length. Now if I want to figure out the radians, I need to get the ratio of A to R, so I'm just going to divide both sides by R. A over R is radians, so that's going to be our theta, like that's our angle. That might look a little bit weird to all of a sudden replace A over R with theta, but like A over R is the number of radians, so that's our angle, that's theta. So theta equals 2 pi. So what does that mean? That means the number of radians in a full circle is 2 pi. What is pi? 3.14, 1592, so on and so forth. And so 2 times that number, which that number obviously is irrational. It goes on forever and never repeats, right? We all know that. But 2 times that number is the number of radians in a circle. So therefore, 360 degrees is equal to 2 pi radians. Does anybody know the world record for memorizing pi? You want to guess? What would you guess would be the maximum number of digits that somebody memorized pi? Just guess. Come on. 150? 300? 800? More guesses. Come on, more guesses. Somebody make a wild guess. 1,000. Whew. 70,000. The world record now, somebody claims to have beaten it, and it was like 250,000 or something like that. But as far as I know, the record still stands at 70,000 digits of pi. Can you imagine? And you think to yourself, how is that possible? And everybody always jokes, especially when you talk to the younger grades, they're always like, oh, that person must not have a life. Like, yeah, that's what they've done their whole life, is sit in their room memorizing pi. Like, no. This person, their brain does not work like our brains. Like, they are just at a different level of understanding. And it's not like they're even memorizing. They just somehow know it, I think. Like, it's insane. Anyway, 70,000 digits of pi. It's pretty wild. Okay, let's do another one. So if I start with C equals 2 pi r, but if I only want a half circle, what am I going to do? Divide both sides by 2. So these 2's are going to divide out to 1. And if I make that my arc length, divide both sides by r. So pi is what? I mean, this makes sense. If 2 pi is a full circle, then...
half circumference of the circle.
Yeah, which is how many degrees?
180.
180, right? So pi is half a circle. I mean, if 2 pi is a full circle, then pi is going to be half a circle. That makes sense. But so our angle in this case is pi, and therefore 180 degrees equals pi. Now, this is really, really important, because especially in the beginning, but even throughout the whole unit, you need some kind of pivot point, some place that you can work off of. And if all you ever remember is that pi is equal to 180, you can use that to figure everything else out that you need. And we're going to do a little exercise on that in a few minutes, where we're going to sort of go through that together, and I'll show you the kind of thinking that I think you'll benefit from when you start working with radians. But this is something that you just need to remember. So I'm going to ask you probably in about 5 minutes, but I'm also going to ask you again in the next lesson, and ask you again when we come back the next day, and ask you over and over again, pi is how many degrees? And I need everybody to remember that it's 180 degrees. And as long as, like I said, as long as you can remember that, then that's your pivot point that you can work off of for everything else. Okay, so we're going to do a little bit of converting, but as I said, this is not really what we are going to be doing moving forward. You're not going to be getting radians and converting them to degrees. I'm not even going to test on this. Like, I'm not going to put it on a test or a quiz or anything. So this is not what you have to be good at. But I think it's still important to kind of know how to convert between the two, and we'll do a learning goal on it for what it's worth. So there's a very easy rule to convert radians to degrees as long as there's a pi in the radian. So this is a number of radians. Looks weird, right? You're not used to it. You will be soon. That's a standard way that we write radians in terms of pi. Okay? And as long as there's a pi in there, you just use this easy rule. Just replace pi with 180 degrees. So 4 pi by 5 radians equals 4 times 180 over 5 degrees, which is what? Anybody have a calculator? $144, thank you. So just that right there, it's interesting. 144 degrees is something we understand. It's between 90 and 180. It's a little bit over halfway. Like, you might not be super familiar with that number, but you would have some idea of how to visualize 144 degrees, don't you think? But 4 pi by 5 radians, you have no idea what that means because you've never seen it before. Just give me a second, guys. You've never seen it before, but it's the same thing. 4 pi by 5 radians is 144 degrees. Like, they're the same angle measurement. Okay, so I quickly want to show you what's actually happening here, because we're not actually replacing pi with 180. Pi is equal to 180, so there is a relationship there, but that's not actually what we're doing. We're multiplying by a conversion factor. What we're actually doing, and this will be important for a couple of things. Like I said, this isn't really what we're doing in this course, is converting. This isn't super important, but there is a worksheet on it. What we're actually doing is multiplying by 180 over pi. That's the conversion factor. And the pi's divide to 1. And we end up with 4 times 180 divided by 5. So that's actually what we're doing. So if you had to convert a radian that didn't have pi in it to degrees, you would have to just multiply by 180 over pi. Okay? How about converting 130 degrees to radians? Well, now that we've seen what we're actually doing, we can do the inverse of that, or the reciprocal, multiply by the reciprocal, and 130 degrees is 130 times pi over 180. Right? So we flipped that ratio. It was 180 over pi in the first place. Now it's pi over 180. And then we always reduce it, always fully reduce our fractions. So this just reduces to 13 pi by 18, which is kind of a weird radian number. And once you start working in radians, you'll agree it's a weird one, but anyway. Any questions on that? So, I hope converting is fairly easy. You'll do a little bit of practice with that in the work afterwards. And you are either replacing pi with 180 or multiplying by 180 over pi, or multiplying by pi over 180, and then reducing the fraction. Yep.
Sorry, where did you get 13 and 18?
I reduced 130 over 180.
Oh,
Divided both by 10.
okay.
Here's another thing, folks. If you have a calculator that can do fractions, then this is going to be a lot easier for you, because you can see radians are often written as fractions. We do not convert these to decimals. Very, very rarely would we do that. So if you've got if you're lucky enough to have a good calculator, which I know most of you do, that can do fractions, then that's going to be a big benefit to you. If you don't, and you're not good at fractions, you may want to go find a calculator and buy one that can do fractions. And I've said this before, you can often find them on sale for like $10. Check Amazon. check Staples, Costco. If you have a Costco membership, those places tend to get good calculators like this one for $10. Otherwise, they're 20 or 25 bucks. I think it's still a good investment. Okay, so here, this exercise to me is the most important part of this lesson. Okay, this is going to help us understand how you are actually going to start working with radians and understanding radians. And if you can start to think this way, then you're going to be off on the right track. So, pi is how many degrees? 180. Thank you very much. I just told you about 5 minutes ago that you all were supposed to remember that. And that's the most important thing. Because if pi is 180 degrees, then pi by 2 is how many degrees? 90. So if you see an angle measure, radian measure of pi by 2, you might think, well, that's 180 divided by 2, which is 90. So I know that pi by 2 is 90. So now you know 2 radian angles. And pi by 3 would be what? 60. How'd you get that? Huh? Divide by 3, right? Take 180, which is pi, and divide by 3. Exactly right. And I hope a lot of you were thinking the same thing. Oh, is that going to be 60? And this is exactly how this works. But as I said, on quizzes and tests, we're not going to see the 60. You're going to see the pi by 3. That's the new number that we're using that means 60 degrees, but it's pi by 3 radians. Is equivalent to 60 degrees. And pi by 4?
45.
45. Who said that? How'd you get that?
Divided 180 by 4.
Did you do that on your calculator or in your head?
In my head.
What's it? Can anybody think of it? Very good. Can anybody think of another way that you could do it?
90 divided by 2.
Pi by 2 divided by 2, or 90 divided by 2 is 45. A lot of people know 90 divided by 2 is 45. Not everybody maybe knows that 180 divided by 4 is 45. Or maybe you divide by 2 and divide by 2 again. Like there's lots of ways that you can do it. But if I take pi by 2 and divide by 2, that's like multiplying the denominator by 2. Right? If I took pi by 2 and divided by 3, I'd be multiplying the denominator by 3. This is fraction math. This is the stuff that you have been fearing since grade 5 and that you have hated. And now you actually have to do some fraction math in your head for the first time in your life for a lot of us. But believe it or not, you're actually going to be good at it. And you're actually going to, maybe for the first time for a lot of you, you're going to actually really get fractions, which is kind of cool. Okay, so you could take pi by 2 and divide by 2 to get pi by 4. 90 divided by 2 is 45. So pi by 6 would be?
30.
Say again? 30. How'd you get that?
Divide 60 by 2.
Yeah, and pi by 3 divided by 2 is pi by 6. Very good, right? Because 3 times 2 is 6, so the denominator becomes 6. 60 divided by 30. What's another way we could do it? I could have divided pi by 2 by 3. 90 divided by 3 is 30. I could have divided 180 by 6 to get 30. 18 divided by 6 is 3. 180 divided by 6, right? Like there's lots of different connections here. Pi by 9 is 20.
Yeah.
So maybe pi by 3 divided by 3. Pi by 12. 15. So how'd you get that?
I guess it's like 120, like 12 times 10, which is 120, and half of that is 60.
Okay, good. So, but maybe you look at this, pi by 6 divided by 2 is pi by 12, so 30 divided by 2 is 15. This is not a norm, this is not, I don't know even why it's on this sheet, but it's not a standard, we don't see pi by 9s very often. We see pi by 12s, pi by 6s, pi by 4s, pi by 3s, pi by 2s, pi, 2 pi. Those are normal ones. We'll talk a little bit about pi by 8 eventually. So these are the, like you recognize those 4 numbers? They're in the special triangles. 90 is often, obviously, an important angle. So these are the important radian measures. Pi by 2, pi by 3, pi by 4, pi by 6. Okay, again, pi is 180. And I know we're doubling up here, but there's a reason for it. So pi by 3 is 60. Don't just sit there passively, folks. Try to think of it yourself as well. So then what would 2 pi by 3 be?
120.
How'd you get that?
So I guess multiply the 60 by 2.
So 1 pi by 3 is 60. 2 pi by 3s is going to be 120. Isn't that what 2 pi by 3 means? It means you have 2 pi by 3s. Like if that's not obvious to you, it needs to start being obvious to you. Like you want to start thinking about it that way. I know that now. I know pi by 3 is 60 because 180 divided by 3 is 60, so I kind of get that. So if I see 2 pi by 3, well, that's 2 60s. So that's 120. So what quadrant is that in? Quadrant 2. So 2 pi by 3 is in quadrant 2. Good. And 3 pi by 3s?
180.
180. How'd you get that?
Well, I thought like you can cross out 3s and then it just equals pi.
Okay, very good. It's also 3 pi by 3s and 3 60s is 180. Like, of course, the math is going to work out, but like it does, right? So 2 pi by 3s is 120. 3 pi by 3s is 180 because you can divide the 3s to 1, but also because it's 3 60s. 4 pi by 3? 240. So how'd you get that?
So, I mean, I just look at the pattern, but I mean, you can also look at it just 4 times 60.
Yeah, like you're counting by 60s now, aren't you? Yeah, so that's good. So we're every time we go up a pi by 3, 1 pi by 3, 2 pi by 3, 3 pi by 3, 4 pi by 3, 5 pi by 3, we're counting by 60s. So 5 pi by 3 is going to be 300, adding 60 more. And 6 pi by 3? 360. And 6 divided by 3 is 2. So that's 2 pi, which we already talked about that 360 is 2 pi. See how it kind of fits? See how we're kind of counting in radians? We're counting in fractions. 1 pi by 3, 2 pi by 3, 3 pi by 3, 4 pi by 3, 5 pi by 3, 6 pi by 3. Right? And we're counting by 60-degree increments. Okay, so again, pi is?
180.
Thank you. So pi by 2 is? 90. So 2 pi by 2? Again, you can cross out the 2's, or 2 90s, which is 180. 3 pi by 2? 270. So that's 3 90s. 3 times 9 is 27. 3 times 90 is 270. 4 pi by 2? 360, which again is 2 pi. What is relevant about those 4 numbers?
Those are the 4 points on the chart. Like in a circle, like 90, 180, 270, 260.
Yeah, so they're the axes of angles in standard position. They're also the where the points on the curves of the base curves start, right? So like if I do a little graph, we start with 0, and then we have pi by 2, because that's 90, and then pi, 2 pi by 2, but we would always write it as pi, and then 3 pi by 2, and then 2 pi. That's not dividing by, that's like it's 0 and it's 2 pi. Maybe I should use a comma. Okay, so again, important radian values. Okay, pi is 180. That was a pretty miserable response. Okay, pi by 4? 45. 2 pi by 4?
90.
So 2 45s, or 2 over 4 is 1 over 2. So pi over 2, which we know is 90. Anybody already feel like they're starting to kind of get like used to these? Like you kind of already know pi by 2 is 90. You kind of already get that. Happens fast. 3 pi by 4. So this is 3 45s. 135. Again, these are common ones that come up. Notice we skipped 4 pi by 4. I think I've always meant to put that back in just to keep it right. So 4 pi by 4 is 180. So 5 pi by 4 is 225. 6 pi by 4, 270. And isn't that 3 pi by 2? 6 over 4 is 3 over 2. So like I'm counting in radians. I'm counting in fractions. 1 pi by 4, 2 pi by 4, 3 pi by 4, 4 pi by 4, 5 pi by 4, 6 pi by 4, which now I know is 270, but I can reduce it, so I would write it as 3 pi by 2. But there are times where you're going to be counting in 45s. So you're going to be doing this 1, 2, 3, 4, 5, 6 kind of thing. This is pi by 2. Okay, finally 7 pi by 4, 315. And 8 pi by 4 is 360, and that's 2 pi. 8 divided by 4 is 2, so 2 pi. Right there is probably the most important exercise of this lesson, because that's what we're actually going to be doing. And yes, we're converting to degrees to kind of have a sense of what the degrees are, but eventually you won't have to do that. But we don't convert this way when we're working with these. We convert this way by thinking about pi being 180 or pi by 2 being 90 and kind of working off of that, as I called it a pivot point earlier, to figure out what the other ones are. If pi by 2 is 90, 3 pi by 2s is 390s, which is 270. Okay, we'll do a couple more examples. You try these. Convert each of the following to radians. Oh, this is a different worksheet from what you have. Give me a second. Okay, we're going to do this question first. Determine the angle made by an arc length of 5 centimeters in a circle with a radius of 8 centimeters. This is a kind of math, we're not going to do a lot of this in this course either, but this is the kind of math that I could actually see being important if you were doing anything working with circles, any kind of engineering, gears. So if you are going into engineering, there's a very good chance that you may do some of this kind of stuff and do more work with circles. There's a lot of interesting math with circles and properties of circles. We just don't do a lot of it in high school. So, determine the angle made by an arc length of 5 centimeters in a circle with a radius of 8 centimeters. So the first thing that we're going to do is we are going to draw and label a circle. And I bet you didn't know that I could draw a perfect circle like that freehand. That's pretty impressive, isn't it? Can you do that? Okay, so I'm going to mark the center of the circle. The radius is 8, and the arc length is 5, so I'm going to try to draw it so that they're kind of in that ballpark of a ratio. And that angle is theta. When you're doing these kinds of questions, I mean, you might sketch it like this, and then you write this, theta equals A over R. Because it might give you theta, and you have to calculate R, but you just use this little formula. That a radian is the ratio of arc length to radius. So that's our formula, and that will solve all these problems. Okay, so with theta equals 5 over 8. And then I just do 5 divided by 8 because we probably want the decimal, so 0.625 radians. In this lesson, when you're doing the homework, it would be appropriate to use that to say what kind of unit you're working in. If you're converting back and forth, you would call it a radian. After this lesson, we will no longer write RAD on everything. It's just assumed everything is a radian. Okay? But for this first lesson, because we're working with degrees and radians, it would be appropriate to include the units. Okay, now we're going to do 2 of these. and I want you to give them a try. So if you can remember how to do the conversion, give it a try. So if you just checked on the other page to convert to radians, we multiply by pi over 180. So it's 120 pi over 180, which is 2 pi by 3. And again, that's 2 times 60. Like if you already knew that 120 was going to be 2 pi by 3, awesome. But if you have to show the conversion steps, that's how you do it. Okay? If you have a calculator that can do this, watch 120 over 180. It gives you the 2 pi by 3. Makes your life a lot easier. In fact, I think this one, there's no real reason to include the pi. You would just write it back in yourself. But look, this one even does have, will write my answer in terms of pi. That's pretty useful. So like I say, if you don't have a calculator that can do that, you might want to get yourself one. Okay, so if you aren't done the second one, do it now. (250 times pi over 180, which is 250 pi by 180, and that just reduces to 25 pi over 18. Again, we almost always leave radian measures in terms of pi as exact values. We're not going to convert that to a decimal and round. We're going to leave it as is. Okay, and there's 3 here to convert to degrees, so go ahead and try that. Okay, so for the first one, I did like the whole show kind of thing. I multiplied by 180 over pi. The pi's divide to 1. You get 2 times 180 over 3. And whether you do 2 times 180, which is 360, 360 divided by 3, which is 120, or maybe you do 180 divided by 3, which is 60 times 2 is 120, it's 120. I know, we just did that. You're like, well, we already know that. We just did it in the last one. That's not the point. The point is the mechanics of the actual converting, right? That's the point. So we already knew 2 pi by 3 was going to work out to 120, but you can see it happen in the math. And because there's a pi in there, you can just replace it with 180, which is what I did the second time. Okay, and that one worked out to 157.5 degrees. And so 3 pi works out to what?
540.
So 3 times 180, which is 540 degrees. Any questions?